So at the Cleveland plant, M&M's plant in Cleveland, they're aiming for a percentage, 21% of orange M&Ms. And so we're going to imagine that we're a technician working at that factory, and every day we take a sample of M&Ms and we look at the proportion that are orange. So to do that, we're going to use this Rossmann Chance app. So click on this and it'll open up this website here. So there's a few things we want to do. We want to make sure that we choose the proportion of orange, and we want to turn on the summary statistics, and we do not want to show the animation. So I want to make sure that that is off and not selected. So we're going to assume that it's working correctly. So the probability of orange will be 21. We're going to do a sample of 50 M&Ms. So if we do a sample of 50, how many orange would we expect? Well, if everything's working correctly, we would expect 21% of 50. So we go 0.21 times 50, and that gives us 10.5. So that's how many we would expect. So 10 or 11, why don't we just go with 11 here, but 10 is quite good too, right? So how did we calculate that? That's n times p. Okay, so np gives us our expected value. So let's see if we get that. So if we come over here and we draw samples, we can count the number that we see. So we just come over here and we look 2, 4, 6, 8, 10, 11. So we have 11 out of 50 for a proportion of 22%, or 0.22. So it's basically exactly what we would expect. Okay, so that worked. Let's do it again. So we're going to draw another sample here. This time we get 2, 4, 6, 8, 9, 10 out of 50 for 0.2. So this is P1 hat, 0.22, then P2 hat is 0.2. They're not equal, but that doesn't surprise us because of sampling error. We don't expect to get exactly 20 or 21% or even 22% every time. It'll vary. But how much will it vary? That's what we want to figure out here with this sampling distribution. So let's do this a few more times to get an idea of the range of these samples. Okay, so we're down here on step 6. We're going to draw samples a few more times. Notice each time we do a sample, we get a dot down here, and it's creating a dot plot. So let's do 2, 3, 4, 5, 6. So notice each time we get a slightly different proportion, and that's okay. We expect that, right? So now we've done 8 samples. Let's speed this up a little bit. And so we can do that by, instead of having a 1 here, we can put in 200. So if I put in 200, what it's going to do is it's going to do 200 samples, each of size 50. So we're going to get 200 more dots in our growing dot plot down here. So I'm going to hit the draw samples, and now we have a pretty good idea of the sampling distribution, how much it ranges. So it is possible to get something as low as maybe 6% or as high as maybe 40%, but the vast majority are pretty close to what we'd expect, about 21, 22, 20%, somewhere in there in the middle. That's where the peak is. Okay, so we're investigating the behavior of p hat. And so what we're going to do is think about the sampling distribution of p hat. That's actually where we have all possible samples of size 50, and we calculate a p hat for each one. And so it's actually a very vast number of dots. It's more than a computer can actually calculate. So the best we can do is do something approximating this sampling distribution. And so to do that, here on step 9, we're going to add 10,000 dots now to our 208 dots that we have. So I'm going to go 10,000. And what this does is it creates 10,000 samples, each of size 50. So we're going to get quite a lot of dots now. In fact, we can't even really see separate dots. They just look like solid bars, but those really are just a bunch of dots, a little bit more than 10,000 dots. So what are the mean and the standard deviation from the applet? Well, the mean is 0.21. Okay, so we have a 0.21 mean there. So we'll put that in. So 0.21. The standard deviation, and notice that the 0.21 is what we expect it to be, right? If it's working correctly, we would expect, 0.21. And the standard deviation is a little bit less obvious. It's 0.058, so we go 0.058. And we also want to double check that with our formula for the standard error. So we'll put that into the formula. So P is 0.21, 1 minus 0.21. And then we're going to divide that by the sample size, which is 50. Okay, so if we pull out the calculator here and do that, so we'll have 1 minus 0.21 times 0.21. Okay, and then we divide that by 50. We take the square root of that. And notice to the third decimal place, if we round to the third decimal place, we get 0.058, which is exactly what we found empirically with the website here, right? So 0.058, it matches up perfectly with the theoretical value. Now, 50 is probably a small sample, right? Because M&Ms are not expensive, and we're working at a factory that makes M&Ms. So maybe we should do 500, a larger sample of, say, 500, to give us a more accurate idea of the sampling distribution here. So what we'll do is change this to 500, okay? And we'll draw samples. And what that's going to do is give us 10,000 samples, each of size 500. And it's pretty amazing how quick the software, the website can do that. And again, this isn't the perfect sampling distribution. This isn't every possible p-hat from every possible sample of size 500, but it's a fairly good approximation for it. So we have 10,000 here, and let's again investigate the mean. So the mean is 0.21, which is exactly what we expect it to be, right? Because the proportion of orange is 21%, or 0.21. Standard deviation, or the standard error here, is a little bit different, or a little bit less obvious. We can write that down as 0.018, and we can test that versus the formula, the theory for the standard error. So we'll put in 0.21, 1 minus 0.21, and then we divide that by 500 this time. So back to the calculator, 1 minus 0.21 times 0.21. We divide that by 500. Take the square root of that. And what do we see to the third decimal place? It agrees exactly with the empirical standard error that we found from the website, 0.018. Okay, so here in step 16, which histogram has more spread? The one in step 10 or the one in step 14? Well, the one in step 10 has a standard error of 0.058. The one in step 14 has a standard error of 0.018. So the one in step 10 has more spread, and that's because it has a smaller sample size. Okay, so we see that the larger the sample, the less the standard error for p-hat. So what I'd like you to do is look at the same thing, but at the Hackettstown factory. So M&M's has another factory. They have one in Hackettstown, New Jersey. And interestingly, at this factory, apparently the proportion of orange is supposed to be 25%. You can read about this if you want. In the footnote here, we have the website to this article about M&Ms. And so I'd like you to try this all again. basically very similar, except instead of 21%, which we see for the Cleveland factory, we're going to have the 25% for the Hackettstown factory. So I'd like you to pause the video and work through this whole exercise here on this page for the Hackettstown factory. When you're done, unpause the video and check your results versus mine. So here for Hackettstown, we need to reset everything. And again, we want to make sure that we have proportion of orange selected. We want to make sure that the show animation is not on. It'll still work. It's just a little bit messier with the show animation. And we want to make sure the summary statistics are on. Then because this is at Hackettstown, we're going to go to 25%. And again, let's start with a rather small sample of size 50. And we'll just do single samples here. Okay, so we're going to do one sample of size 50 M&Ms from the Hackettstown factory. So we hit draw samples and we look at the results. Actually, let's answer this question over here before we analyze those results. So if you take a sample of 50, how many orange would you expect? Well, we're expecting about a fourth of those 50 to be orange. Okay, so it's N times P. So go to the calculator here. So a fourth of 50, we go 0.25 times 50, about 12.5. Okay, so either number here would be fine, 12 or 13. Let's go ahead and go with 13 here. So we expect about 12 or 13 orange each time we do this. So let's see if that's what we get. So over here, we have 3, 6, 9, 11, 13, 15. So we didn't get 13, we got 15. Okay, so we got 15 over 50. So we're going to go 15 divided by 50. We get 0.3, which is what it shows here. We're at 0.3. Okay, so our first p hat was 30% or 0.3. Do we need to shut down the factory and recalibrate? No. The expected value is 13, but we know it's probably not going to be exactly 13 every time. It's going to bounce around a little bit. Let's do this again and see what we get on our second one here. This time we had 2, 4, 6, 7, 8, 9. So I'm just looking at the orange here over on the side. So again, 9, 10, 11, 12. Okay, so this time we had 12. We were expecting 13. We got 12. Is that a problem? Okay, so again, we pull out the calculator. We go 12 divided by 50.24. Sorry, I miscounted those. It's not 12. Okay, this one is not 12. Let's see here. So we had 2, 4, 6, 7, 8, 9. My apologies. Okay, so let me recalculate that p hat. So we have 9 divided by 50 for 18%. That's more like it. Okay, so we have 18 here. Do we have to stop the factory and recalibrate? 18 is a little bit lower than 25%. But probably because of sampling error, we'd expect p hat to bounce around a fair amount. So they're not equal, right? 18% does not equal 30%, and we're not surprised by that either because of sampling error. Okay, so the sample proportion will vary from sample to sample because of randomness, but we don't expect it to be too far from 0.25. So to help us understand the behavior of p hat, let's do more samples, right? So instead of just 2 samples, let's do 10,000 samples. So we're going to go 10,000, and we hit draw samples. And now we have so many dots there, they become solid bars. Okay. What are the mean and the standard deviation for this graph here? So we have 0.25. We can see that right here from the website, 0.25. That's not surprising because it's 0.25, right? So if 25% of the orange of the M&Ms are orange, then we would expect the middle of the sampling distribution to be about 25%. What about the standard error? 0.060. Okay. What is the theoretical formula for it? Well, the formula is P1 minus P over N. So we go 0.25, 1 minus 0.25 over 500. I'm sorry, 50. Sample size here is 50. Okay. So we go 0.25 times 1 minus 0.25. Okay, and then we divide that by 50. We take the square root. What do we see? 0.061. Okay. It's pretty darn close to the value we got in the app, right? So if we rounded to the second decimal place, it would be exactly the same thing, right? So I'm not really concerned by that because we only did 10,000. 10,000 sounds like a lot, but compared to the actual sampling distribution, that's a very small approximation. So that's close enough. That's very close, right? Okay, so again, just like we saw with the Cleveland example, 50 is probably a small sample size. So let's do this again with sample size 500. Okay, so we're going to do the same thing. We're going to do 10,000 samples, each of size 500. It's pretty amazing how fast the software is on this. If we look at the distribution here, we can see that looks quite normal, right? Not perfect, but again, if we wanted to, we could do another round of 10,000 and it would start to even off these rough edges. And so we see something very similar to what we have over here in the worksheet. So let's look at the mean. The mean is 0.25. Okay, so we go 0.25. Again, not surprising because that is the proportion of orange at the plant. Standard deviation 0.018. So we go 0.19, 0.019. Does that agree with the theory? So the theory is square root P, so 0.25, 1 minus 0.25. This time we're doing samples of size 500. So pull out the calculator here. So we go 1 minus 0.25 times 0.25. Take the square root of that. I'm sorry, I did that wrong. Do that again. So 0.25 times 1 minus 0.25, which is 0.75. Forgot to divide first. So we have to divide that by 500. Then we take the square root of that, 0.019, which is agreeing perfectly with the empirical result that we got by using our website over there, right? So the formula works. The formula for the standard error really does work, okay? And we see it here matching up with the empirical results quite well in several cases. Which histogram has more spread, the one in step 10 or in step 14? The one in step 10 has more spread. If you look at the histogram here, it ranges all the way down to about 8%, all the way from 8% up to, even the high 40%. Whereas with this one, it doesn't really look like it's very often getting over 30% very much, or down below maybe 18%. Very rare for that to happen. So, and that's also, we can tell that here by the standard error for the second histogram is much less than the standard error for the first histogram up there. So the one in step 10 has more spread, and that's because it has a smaller sample size.